Good morning. Today we are going to cover rectification. In today's class, we are going to see the half-wave rectifier, the full-wave rectifier using two diodes and a central tap transformer, and also we are going to see the full bridge rectifier in which we have to use 4 diodes. What I want to show you before we even begin is that I created a simulation for you guys using multisim. What I want to show you first is that I want you please to go after this class. I mean, of course, we are going to be meeting in the shop, but also I want you to have a chance to go into Iconestoga. So when you go to Iconestoga, you will get from the content in your course. I want you to go into something which is called lab simulations. Okay, so at this point in time, under lab simulations, you have your workbook, which is right there. And then you have something here under lab simulations, which is called, okay. Let me do it once more, go to the content, lab simulations. From lab simulations, please go to project number 3, rectification. You can see that under this project, it says for practice only. So this project doesn't count towards your marks. However, if you decide to do it, if you decide to give it a try, it's gonna put you in a better position to understand what is it that you are doing in the shop. Okay, so I'm gonna click here. And when we click on this project, you will be able to see a link for the half-wave rectifier, full-wave rectifier, center tab, and for the full-wave bridge rectifier. So I'm gonna click on the link so you can see what you are going to observe. By clicking the link, you will have immediately an oscilloscope with a bunch of values. Some of the values on the oscilloscope, it tells you how the oscilloscope is calibrated. You can see that on the, like right here on the top, on the vertical position, going from on the vertical position where you measure your voltage, going vertically, you have 5 volts per division. Okay, so if I were to stop the simulation, because I have 5 volts per division, I would be able to count my divisions and determine what is my max voltage. Okay, so I would be able to count here 1, 2, 3, 4, 5, 6, 7. So 7 times 5, that's 35 volts already, as you can see here. Also, as I hover over the different divisions, you can notice on the oscilloscope that it displays how many volts I have. Okay, so once you bring this pointer all the way to the peak voltage, it will tell you what is the actual peak voltage that you have for this simulation. Okay, in this case is 38.8 volts. So it is important that you get familiarized with the idea of learning how to read voltage on the vertical position using the voltage division. Also, you can see that it has the time right here, and it has the time, which is the time division on the horizontal scale. It is 5 milliseconds per division. Also, I included like a few different values that are being measured automatically for you, like max voltage, your RMS voltage, and you may wonder why you have an RMS voltage, and we'll get into that in just a little bit. Okay, that's called the ripple voltage in a pulsating DC rectification. And then we have the average voltage, which is the DC voltage. And of course, this is the half-wave rectifier at 60 hertz. And you could do your whole lab using this. But because we have been given the time to do the lab, like in the shop, in the actual shop, I'm going to be expecting that you are going to be connecting your circuits, because even when this can give you a pretty good idea on which value you should be getting from your project, this is not how we are supposed to do our projects. Our projects are to be done in the shop, but this will put you in the right perspective so you can understand what's going on. Because in the shop, you don't have the ability to see how is it that the current is moving through the circuit. While here, you can see how the current is moving. Okay, that's one of the advantages of using this simulation software. So I will leave it completely up to you. You will be able to see the full wave rectifier and how is it that the current move whenever we have to diode with a center tap transformer, and also the full bridge rectifier. And then you will be able to see how is it that the four diodes are working all together in conjunction in order to produce that full wave rectification in the circuit. Okay, so what I'm going to do now is that I want to show you also something else that I want you to be able to do on your own, okay? Content, please review. Today's class is going to be posted. I'm going to have to edit it, of course, and then it's going to be posted. And take the time to watch this video about diodes. And then there's two other presentations about semiconductors. One, which is about semiconductors, something that you cover in level 1, because you already covered this section in level 1. We don't have to cover all this slide by slide. So just please take the time to refresh your memory about that level 1 topic. Also, we have the PN junction, which is what a diode is. You know, like we take one P, which means a positive semiconductor, and then we take a negative semiconductor and we join them and we create the PN junction, which is a diode. So please take the time and go through this information as well. And I also decided to include a little presentation about junction diodes that comes from Electronics for Electricians, which is a book also produced by Delmars. And it's just to give you like additional information in case you need that additional information, because everyone have a different way of learning. And then there's also another like a small PowerPoint, which is what we are doing today. But I'm not going to be using this PowerPoint. This PowerPoint is only here just to give you some additional information as well. Okay, so that way you are going to be able to see like, okay, like if I have a half-wave rectifier, I have a full sine wave, and then that sine wave, which is represented by this circle, is going to go through the diode, and only the positive signal is going to go through that diode. Because of when the diode is forward biased, the diode is going to behave as a closed switch, and then it's going to allow the positive pulse to go through. Now, when the diode, when this signal becomes negative, then the diode is going to become reverse biased, and then the signal is going to be blocked. Okay, once the signal is blocked, then of course we don't see any voltage. Now, this halfway rectifier is going to have a few different values, like the value, like if we want to determine the value of the voltage which is being applied to the resistor here, we are going to use a formula. And in just a bit, we are going to be getting into that formula, okay? So let's do the following now that we have the halfway rectifier on the screen. So what I'm going to do is that we are going to get into the calculations for the halfway rectifier. So as you were looking on the PowerPoint, if we have a halfway rectifier, okay? So let's say that we have the following voltage on this halfway rectifier. Let's use that the input voltage is going to be 12 volts AC at 60 hertz. So it's 12 volts at 60 hertz. So now we want to be able to determine how much is the voltage that we are going to have right here on the resistor. In order to do that, what we are going to do is that we are going to take, we are going to use the following formula. Okay, so something weird is happening to my phone. I don't know what's happening with all this technology. Okay, I think it's Zoom. Okay. I apologize for that, guys. I'm just having my telephone, like, that's what I'm using for my input, like flashing in and out. So what we are going to have here is that this voltage here, which is the input voltage, is called the RMS voltage, okay? So my RMS voltage ERMS is equal to 12 volts. That's very important to keep in mind. Now, as we mentioned before, here we have our positive and negative voltage. Remember that on this side of the diode, we have our anode and cathode. Remember, please, that the anode is positive and the cathode is negative, right? I'm just going to draw the positive signal. So when my signal is positive, my signal is going to go through, but when my signal is negative, the signal is going to be blocked. Okay, so that's how the signal is going to be displayed. Okay, so I don't know if it's Zoom that is giving me a hard time or my telephone. Okay, so I'm just gonna. Then what's going to happen is that there's a formula that says that this value here, this voltage here, is called E average. Okay, so that's an important word to keep in mind, because I want you to be able to differentiate between E RMS, which is here, and the E average, which is the rectified voltage that we have after the diode, and that is the voltage that is being applied to your resistor here. okay? So that E average is going to be equal to our ERMS this is very frustrating. I apologize for that. My telephone doesn't want to work. I don't know if something about Zoom or if this is something about, okay, so let me see if it's gonna do it now. E average is equal to my E RMS times 0.45. So when we do that, we are going to be able to obtain our voltage value. So how much is that right now, please? Can you please do the calculation and let me know?
$5.4.
Perfect. So it's going to be 5.4 volts. Now, this 5.4 volts, that's already DC voltage. But that voltage here is called pulsating DC. Okay. Now, let's say that we have a 10 ohm resistor. And if we have a 10 ohm resistor, and I ask you, so, okay, so how much is the current that we have through the resistor? The value that you are going to use for that current is going to be your 5.4 volts, because that's the voltage which is being applied to the actual resistor, okay? The voltage was already rectified. The signal was already rectified and converted from AC that have a positive and a negative signal to DC that flows in just one direction. So if we were to use Ohm's law,
E divided by R.
so how many amps do we have?
50.4, is that right?
Much? So it's going to be my 5.4 divided by 10.
Yeah, 50.4. Or did I do that wrong? Well,
0.54.
yeah,
Perfect.
that's right.
0.54.
Yes, right.
Or you could say, listen, we could say we has 0.54 amps, right? Remember that you can always say that we can always skip this decimal point. 1, 2, and 3 spaces, and say that we have 440 milliamps, because that's another way in which we can express this quantity as milliamps. Any questions about this, about the halfway rectifier? Now, on this halfway rectifier, we also has what is called a ripple voltage. The ripple voltage is not more than the amount of AC voltage which is present in the DC signal. Because this is pulsating DC, okay, and not a flat DC line, we are going to have a small amount of ripple voltage. Something that I want to give you, okay, so I'm going to be giving you like a few, okay, let me get that for you. just give me a minute here, and then I'm going to be giving you like a few factors in order for you to determine that ripple voltage. Just give me 1 second here so that I can show you on this. Okay, guys, it seems that, hello, can you hear me? Okay, perfect. You can hear me. Sorry, guys. I apologize. It seems that technology today, I'm a tech guy, and technology is conspiring against me today for some reason. My computer just shut down. So I'm rebooting my computer back home. I'm gonna be posting. We're not gonna waste any time. I'm gonna be posting this video. Almost there. So perfect. Okay, so what I want to share with you, I wanted to share one page, which is, okay, can you see that page now? So on this page, what I want you to be able to see is that here, this is something that you're going to be using in level 3, but I'll give you this page today in the shop so you can have a copy of this, okay? So if we have a single phase rectifier, and all these, the first 4 are, well, actually the first 3, which is the ones that we are going to be doing, are single phase rectifier. The supply voltage on a single phase rectifier, which is half wave, is line to line, okay? Because we just have a transformer, line 1 and line 2. Now, in order to calculate the average voltage, that's the value that I was giving you, is we are going to multiply that line to line voltage times the 0.45. That's why I told you that what we were doing was that we were taking our 12 volts, which is the line-to-line voltage, and we multiply by the 0.45, and that was our average voltage. Okay, and the average voltage is the amount of DC that we have after the diode. Now, the amount of AC that we have in the circuit after the diode is called the ripple voltage. Okay, so that ripple can be found by multiplying our 12 volts by 0.54. There is another lengthy formula that we can use, but for today, we are just going to be using like this, just these 2 factors, 0.54 and 0.43 when we have a full wave rectifier. And then next week, because we are going to be using capacitors, and the ripple voltage is going to change, and we're not going to be able to calculate your ripple voltage using these factors anymore. Okay. So your peak voltage, and the reason why it says here peak inverse voltage is because you have to keep in mind the following. Whenever you have a diode, okay, so remember that the diode is going to be, when it has the positive signal, the diode is going to be forward biased. But when the diode is blocking the negative signal, then it's going to be reverse biased. So it is important to be able to know how much is going to be our peak inverse voltage, which is, in other words, also our peak voltage. Like, just notice that the peak positive voltage and the peak inverse voltage are equal. So if I were going to ask you how much is the peak voltage in this signal, it's going to be the same thing. It's going to be the V line to line, which is the RMS value, times 1.414, which is not more than the square root of 2. Okay. The reason why I was going to say we want to be able to determine that peak inverse voltage, because when we are selecting diodes, we have to be able to know what is the maximum voltage that the diodes can block. Because if we exceed, if we go beyond that peak inverse voltage, the diode will burn out. So that's why that in this chart, the calculation is stated as PIV, as that peak inverse voltage, just to fix in your minds that you always have to be mindful of the fact that you cannot exceed the diode's rating. So any questions about the half-wave rectifier? Not at all. I want to ask you one last question. So when we calculate the ripple voltage for the half-wave rectifier, how much was that ripple voltage? Now this voltage here, you told me was 5.4. I'm gonna write it on the top. And that was DC. And how much it was the ripple?
6.48.
Okay, 6.48. We could round it up to 6.5, but that's fine. And remember, this voltage here is AC. If I take my voltmeter, I am going to measure this value with my DC meter, and my DC meter is going to display that value. Now, when I am going to measure my ripple voltage, I have to set, or I need to have my setting on AC. Otherwise, I won't be able to detect that voltage. So that's very important to know, because that's something that you are going to be doing in the shop today. Now, let's go to the full wave rectifier with 2 diodes. Let's jump into there now. So in the case of a full wave rectifier, in this case, we are using 2 diodes. We still have line 1 and line 2. So this is line 1 here. And the other one is line 2. But now we have a center tap, okay? A center tap in order to serve as our common point. So that symbol, which is the ground symbol, means that that is a common connection point throughout the circuit. I want you to notice also, even when it's not in there, that's something that you did last week or the first time you came to the shop, you were able to notice when you were doing project 2 that there's 180 degrees out of phase component between line 1 and line 2, which means that when line 1 is positive, like it shows here, when this is positive here, at the very, very same exact moment, line 2 is going to be negative. Okay, so your line 2 was here. Well, I'm gonna put line 2 where it has to be, okay. That's gonna make things easier to understand. So line 2 at the same moment down here, it have a negative signal. And then when line 2 becomes positive, line 1 at the very same moment is negative. They are 180 degrees out of phase with each other. If that wasn't the case, if they were in phase, we wouldn't have any potential difference between line 1 and line 2 then. And so let's say now that we have 12 volts between line 1 and neutral, and that we have, of course, 12 volts, okay? They need to be balanced between line 2 and neutral. If we were going to take a look back at the table that I was showing you earlier, at this table here, I want you please to notice here, okay, so let me scroll this up a little bit. It says single phase, full wave, 2 diodes. 2 diodes, it's what we are doing here. We have 2 diodes. And by having the 2 diodes, in order to determine now our average voltage, we have to take the volt line to neutral. What it means is that we are going to be taking any of these 2 voltages. not both. So we know that between line 1 and line 2, we have 24 volts. But in order to determine what's going to be the amount of DC voltage which is being applied to the load, we have to use line to neutral voltage in the equation. So when we do that, and we take our 12 volts in here, now we have again 12 volts times 0.9. How much is it going to be our DC voltage that we have now?
$10.8.
Perfect. It's 10.8 volts. So I'm going to write it down on the top here. So now this 10.8, how are we going to be able to measure this 10.8 with a meter? Can we measure that with a meter? Okay, so that's DC voltage. That's 10.8 is DC voltage, which is the voltage that we are putting through the load right after line 1 and line 2 has been rectified by 2 single diodes. Okay, so this is DC voltage. So we measure this with the DC meter. While if we want to determine the ripple voltage, then we are going to take the same 12 volts and we are going to multiply by 0.43, and how much voltage AC we are going to have, which is our ripple. Anybody care to comment? I'm waiting.
5.2.
Perfect, 5.2. Thank you. And that voltage will be measured with an AC voltmeter. So today you have to be mindful of the fact that you have to switch your meter from DC to AC in order to measure average voltage and ripple voltage. Okay, so let's keep moving then. Now, your peak inverse voltage will be calculated. Okay, this is an important one. Your peak inverse voltage will be volt line to neutral times 2.828. But we don't have to worry about this, okay? We don't have to worry about this at this point in time. But that's how you would be able to find your peak inverse voltage. Also, something which is important to know, if you were going to calculate the amount of cycles per second that you have in your DC signal, then you are going to take the frequency of the line and multiply by 2. In other words, your 60 hertz times 2, that means that on this signal, okay, which is our full wave rectification, we obtain 120 hertz. That's going to be the frequency that we are going to see through the load. Let's keep moving then. Any questions about this, of the calculations or anything else? So let's move on to the next one, to the last topic of the day. And then I'm going to prepare this video so you can have it as a reference going forward in case you need to revisit any of this information. So the last component will be the bridge rectifier. In the case of the bridge rectifier, it uses 4 diodes. And if you are wondering, so how is it that these core diodes, but by being interconnected the way they are causing that by having only line 1 and line 2, please notice that we are not using a center tap anymore. What is the advantage? It is cheaper to buy diodes than to build a transformer with a center tap. A transformer with a center tap is pretty much two power sources on the same transformer. So if I were going to use the same voltage, the same 12 volts, still I'm going to be able to get just with half the windings, I'm going to be able to get here my 10.8 volts anyways. If we go back to this here, to the calculations, now for the single phase full wave bridge, in order to determine the values, like the supply voltage will be line to line, just the same way we were doing when we calculated the half-wave rectifier. It's going to be line to line, okay? So in this instance, if we have our 12 volts, we already know that 12 times 0.9, we already learned from here, from the two diode fashion, that that was going to give us 10.8 volts. And we already learned that how much it was going to be the ripple? By taking our 12 volts and multiplying by 0.43?
6.2.
6.2?
Yeah.
Perfect, thank you. Perfect. Okay, and again, you know, like we would be able to calculate what is the peak inverse voltage, which is like the maximum amount of voltage which is being applied. So the diode's rating for the peak inverse voltage doesn't have to be, they don't need to have the high rating that they would need to have, like in the case of a two diode system. In spite of the fact that we are saving lots and lots of money by using a smaller transformer in order to be able to get the 10.8 volts DC in here. Any questions about that? If you are wondering, how is it that this rectifier is actually working, you know, because it has 4 diodes. That's why that under the content I posted those lab simulations, so you can have an idea on how is it that that rectifier is working. If you want, you have the control to see it, to see the simulation at a very slow speed. Then you would be able to see, you would be able to slow down the simulation. On these controls, on the simulation speed and current speed. And then you would be able, how is it that the current is moving from the power source through the diodes? So you can see that when the signal is being rectified, okay, so you can see that we have from this side, let's say this is line 2, this is line 1. This is line 1 here, and this is line 2 here. Okay, so line 2 is feeding the circuit, currents goes, do its work, and then it returns through this line, through this diode, back to the source. Okay, it returns to line 1. I'm gonna accelerate the simulation a little bit. Now you can see how everything changes. Now, line 1 is the one that is feeding the circuit, that is feeding this light bulb. So now that the current is going through this diode, it does its work, and then it returns on the opposite diode back to line 2. So you can see that at any given point in time, only these two diodes are behaving as rectifiers, and these two diodes are behaving as returns, the return path. Anyways, guys, so this is it for today. So I will see you later in the shop. Do you have any questions about today's class? Everyone is quiet, so I guess that no one have any questions. Well, so see you soon. See you in the shop. Have a safe and nice drive. Somebody asked me what labs we are going to be doing today. That's going to be lab number 3 and 4. So that's what we are doing today. So for those doing lab number 4 today, I will give you an additional formula to calculate ripple voltage, but I'm going to do that in the shop. Okay, I'm going to do that on the board. So see you soon, guys. Have a safe drive.